Welcome everyone. Imagine you are holding a jet engine in your hands. It has an intake where raw air enters, a core where all the combustion and transformation happen, and an exhaust where power comes out. Now, replace air with data. Replace combustion with mathematical computation and replace power with predictions, decisions and intelligence. That's exactly what a deep learning system is, a data engine. Today we are going to open up this engine, look inside every component and understand how it actually works. From the raw data that goes in all the way to the intelligent output that comes out. As you can see on this slide, the engine has three key sections. The input layer where raw data is ingested and transformed, the hidden layers, the neural core where the actual thinking happens, the output layer where the model delivers its final answer. By the end of this presentation, you will not only understand what deep learning is, you will understand why it's completely changing the world around us. Let's fire up the engine. The shift from manual engineering to automatic pattern recognition. Before we go deeper, we need to understand a fundamental question. What is the actual difference between traditional machine learning and deep learning? Look at the left side of this slide, traditional machine learning and a cat. If you want a classic ML model to recognize a cat, you, the human expert, have to sit down and manually define what a cat is in mathematical terms. Ear angle, nose width, tail curvature, body proportions, you measure, you label, you engineer every feature by hand. This is called manual feature extraction and it is incredibly slow, expensive and brittle. What happens when the cat is lying down or wearing a costume? The model breaks. Now look at the right side. Deep learning. You just show the model millions of cat photos. No manual measurements, no human definitions. The model's layers automatically learn to detect edges, then shapes, then ears, then the full concept of cat all by themselves. Now, if we talk about the real world examples, think about Google Photos. You can search bitch in your photo library and it instantly finds every bitch photo. Even once you never tagged, nobody at the Google sat down and measured sandiness. The deep learning model figured it out automatically from the billions of images. Key takeaway. Machine learning learns from data. Deep learning learns patterns from massive data automatically. This is the superpower that changed everything. Now let's come over up from diagnosing the right approach for the right data. Now that we understand the philosophical difference, let's get practical. When should you actually use machine learning versus deep learning? Because choosing the right wrong tool is one of the most common and costly mistakes in data science. Let's walk through this comparison table. Data requirement. Machine learning works well with smaller structured datasets. Hundreds to thousands of rows, deep learning needs massive amounts of data, often millions of examples to truly shine. Feature engineering. With ML, a domain expert manually selects which comments matter. With deep learning, the network discovers relevant features on its own. This is a double-edged sword, powerful, but requires more data to compensate. Performance. Both can perform well, but deep learning scales dramatically with data. The more data you give it, the better it gets. ML tends to plateau. Training speed. ML models train in minutes to hours. Deep learning can take days or weeks on powerful GPU clusters. Primary use case. ML excels on structured tabular data like a spreadsheet of customer transactions. Deep learning dominates on unstructured data, images, audio recordings, natural language text. Real world decision. Example: if a bank wants to predict loan default risk from a customer database with 50 columns that use ML, it's faster, needs less data, and the features are already structured. But if Netflix want to recommend shows based on what you watch, how long you pause, and your search history, that's deep learning territory. The bottom line: use the right engine for the right road. Now we come up towards the next slide. The anatomy of an artificial neural network. Now let's open up the hood and look at the engine itself. An artificial neural network, or NNN, is inspired loosely by the human brain, not in a science fiction way, but in a mathematical way. It's a system of connected nodes organized into layers. There are three types of layers, and you can see all of them in this diagram. The input layer on the left receives raw data. In this example, the input is a dog image broken down into thousands of individual pixel values. Each pixel values a number. A 200 by 200 image becomes 40,000 input values. The hidden layers in the middle are where the magic happens. Each node in a hidden layer receives values from the previous layer, applies a mathematical transformation, and passes results forward. In early layers, nodes detect simple patterns like edges and corners. In deep layers, they detect complex patterns like paw or snout. The output layer on the right produces the final answer in this case. The network gives a probability for each possible label, cat or dog. The highest probability wins. Now, real world example. When you use Google Lens to photograph a plant and identify it, an NNN is doing exactly this. Raw pixels go in thousands of hidden layer transformations happen in milliseconds, and Monstera deliciosa comes out the other side. The brilliance of this architecture is that the network learns which connections matter. We don't have to tell it. Now, inside the hidden layer, how a single neuron processes data. Let's zoom in even further. We've seen the full network. Now let's look at a single neuron. Because understanding this one unit unlocks the entire mystery of how these networks actually learn. A single neuron does four things in sequence. Step 1: receive inputs. The neuron receives signals from every neuron in the previous layer. Each signal comes multiplied by a weight, a number that represents how important that connection is. Strong connections have high weights. Weak ones have low weights. Step 2: add bias. A bias value is added to shift the result. Think of it like the neuron's default opinion before seeing any data. Step 3: apply activation function. This is the most critical step. The activation function decides whether this neuron should fire or not, and how strongly. Without this, the entire network would just be doing boring linear math. Incapable of learning complex curved real world patterns, the activation function introduces non-linearity. Step 4: send output. The result gets passed to the next layer. Real world analogy: think of a neuron like a committee member voting on a decision. Each piece of incoming information has a different weight. Some evidence matters more than the others. The activation function is the member's judgment threshold. Is this evidence strong enough for me to vote yes? The most popular activation function today is ReLU, rectified linear unit. It's beautifully simple. If the value is negative, output is 0. If positive, output as is. This simple rule applied across millions of neurons enables networks to model extraordinarily complex real-world phenomena. Now, The learning loop, measuring error and steering towards accuracy. Here's the question everyone eventually asks. Okay, I understand the structure, but how does it actually learn? How do you weights get set to the right values? The answer is a process called backpropagation, and it works in a continuous loop with four steps. Look at the diagram. Step 1, prediction. The network makes a guess. It processes the input data through all its layers and outputs an answer. Step 2, loss function. The loss function measures exactly how wrong the prediction was. This is the network's report card. Common loss functions include mean squared error for regression problems and cross entropy for classification. Step 3, optimizer. The optimizer is the engine that uses the error measurement to figure out which direction to adjust every weight in the network. The most fundamental optimizer is gradient descent. It calculates the slope of the error and nudges every weight slightly downhill towards lower error. Modern variants like Adam are smarter and faster. Step 4, update weights. All weights across the network are adjusted slightly. Then the loop repeats with the next batch of training data. Real world analogy. Imagine learning to throw darts. Your first throw misses. That's the prediction error. You observe how far off and in which direction. That's the loss function. You adjust your stance and aim. That's the optimizer. You throw again. After thousands of throws, you become accurate. The network does this millions of times per training session. This loop is the heartbeat of deep learning. Architecture 1, Artificial Neural Networks, NNN. Now we are going to explore four distinct neural network architectures, each designed for a different types of problems. Think of them as different engine designs, a car engine, a jet engine, a rocket engine, same principle, very different use cases. Architecture 1, ANN, Artificial Neural Network. The NNN is the foundational design. It consists of fully connected, dense layers. Every neuron in one layer connects to every neuron in the next. Look at the diagram. Tabular data goes in on the left, rows and columns from a spreadsheet. Gets processed through two hidden layers and a prediction comes out on the right. NNNs are the standard choice for structured tabular datasets where data comes in rows and columns and you've already identified your features. A real world example, a real estate valuation. Imagine you are building a model to predict house prices. Your dataset has come columns like square footage, location, number of bedrooms, age of building, distance to metro. Each row is one house. And NNN takes these numbers in the input layer, finds complex combinations and interactions between them in the hidden layers, and predicts the price in the output layer. Companies like Magic Bricks, Housing.com, and Zillow use exactly this kind of model to give you instant property valuations. The model has been trained on millions of past sales and can estimate a fair market price in milliseconds. When to choose ANN? Structured data, regression task, predicting a number, or classification task on tabular data. Second, architecture. An NNN treats every input as independent. It doesn't care if two pixels are neighbors. But for images, neighboring pixels are everything. The relationship between adjacent pixels is what creates edges, shapes, and objects. Architecture 2, CNN, Convolutional Neural Network. CNNs are specifically built for visual and spatial data. Instead of fully connected layers, CNN use convolutional layers that slide a small filter also called a kernel, across the image scanning for local patterns. Look at the diagram. The filter scans across the input image and at each position it checks is this pattern. Edge, curve, texture present here. The output of this scan is a feature map, a compressed representation of where each pattern was found. Early CNN layers detect simple patterns, horizontal lines, vertical edges, color gradients. Deeper layers combine this to complex patterns. Eyes, wheels, letters. If we talk about the real world examples, face recognitions on your phone. When you unlock your iPhone with Face ID, a CNN is scanning your face in real time. It's not memorizing your photo, it's memorizing the spatial relationships between your facial features, how far apart your eyes are, the curve of your jawline, the shape of your nose bridge. Similarly, in hospitals, CNNs analyze chest x-rays and MRI scans to detect tumors, fractures, and disease, sometimes catching anomalies that radiologists miss on first glance. When to choose CNN? Any image, video, or special data task, face recognition, medical imaging, satellite analysis, quality control in manufacturing. Now, architecture 3, recurrent neural networks. Standard NNs and CNNs have no memory. Show them the data point A, then data point B. They process each completely independently, but language doesn't work that way. The word bank means something completely different in I went to the bank for a loan versus I sat on the river bank. Context, the word that came before, changes everything. RNNs are RNNs are engineered for sequential data. They haven't an internal hidden state, represented as HT in the diagram, that persists from one time step to the next. When processing word 5 in a sentence, the RNN still remembers information from words 1 through 4. This memory flows forward through time. Look at the diagram. Each processing unit feeds its output into the next unit. Time flows from left to right, and the hidden state carries context across the entire sequence. Here, the real world example is Google Translate. When Google Translate converts the cat sat on the mat into Hindi, it doesn't translate word by word. An RNN processes the entire English sentence sequentially, building up a contextual understanding, and then generates the Hindi sentence word by word using memory of what came before to ensure grammatical coherence. Real world example 2 is stock price prediction. Hedge funds use RNN to analyze historical stock price sequences. The model remembers price patterns from the past 30 days to predict what tomorrow's movement might look like, essentially treating stock prices as a time series conversation. When to choose RNN? Text, speech, time series, data, sensor readings, music generates financial forecasting. Architecture 4, Transformation Transformers. RNN were powerful, but they had a critical flaw. They process sequences one step at a time. For long text, early context could fade, training was slow, and scaling was hard. In 2017, Google researchers published a paper called Attention is All You Need, and it changed everything. The transformers don't process sequences step by step. They process the entire sequence simultaneously using a mechanism called attention. Every word directly attends to every other word at once, regardless of distance. Looking at the diagram, the input sequence goes in on the left. The attention mechanism assigns weights to every pair of words. How much should word 3 pay attention to word 7? Capturing long range relationships instantly. The result is a rich contextual representation that powers the output. This parallel processing makes transformers dramatically faster to train and scales to hundreds of billions of parameters. The real world example is ChatGPT. ChatGPT is powered by a transformer model called GPT. When you ask it a complex question, it doesn't read your message word by word. It processes your entire question simultaneously, attends to the relationships between all your words, and generates a coherent, contextually accurate response. The same transformer architecture power Google Search, GitHub Copilot, which writes code for you, and real-time speech translation in Microsoft Teams. When to choose transformers? Anything involve language, large-scale text understanding, code generation, multimodal AI, or when you have massive compute and data. Powering the modern world industry applications. We've covered the architecture. Now let's zoom over and see where deep learning is already running the world around you right now today. Healthcare. AI models are analyzing medical images, MRI scans, CT scans, retinal photographs to detect cancer, predict diseases, and flag anomalies. In some benchmarks, deep learning models have matched or even surpassed the diagnostic accuracy of trained radiologists. Companies like Google DeepMind have built models that detect over 50 eye disease from a single retinal scan. Finance. Your bank's fraud detection system is powered by deep learning. The moment your card is swiped, the model checks the transaction against hundreds of behavioral patterns, location, merchant type, in under 100 milliseconds and decides in this you or a fraudster. MasterCard and Visa processes billions of transactions daily this way. E-commerce. When Amazon shows you customers also bought, that's a deep learning recommendation engine analyzing your browsing history, purchase patterns, and comparison behavior to predict what you are likely to want next. These recommendation engines drive over 35% of Amazon's total revenue. Now, social media. Your Instagram and YouTube feeds are curated in real time by deep learning models. Every scroll, every pause, every like is a data point the model uses to predict what will keep you engaged. The same CNN technology also powers the facial recognition that auto tags your friends in photos. Deep learning isn't coming, it's already here, woven into the fabric of daily life. Let's do a full teardown of one of the most complex real world applications of deep learning, the self driving car. A self driving car is not running one AI model, it's running multiple deep learning models simultaneously, each specialized for a different task, all coordinated in real time. CNN object detection. The cameras mounted around the car feed images into a CNN every fraction of a second. The model identifies and classifies every object in the visual field: pedestrians, other vehicles, cyclists, road signs, barriers. It knows where they are, how large they are, and whether they are moving. CNN traffic light classification. A separate specialized CNN focuses specifically on traffic lights. detecting their color and state, red, yellow, green flashing, and feeding that information into the decision system. Spatial models, lane detection and boundary mapping, using data from cameras and LiDAR sensors, laser range finders. The system maps road lanes, shoulders, and boundaries in 3D space, allowing the car to understand exactly where it is on the road. All of this happens simultaneously, processed in milliseconds, and feeds into a master decision system that controls steering, accelerating, and braking. Real world companies, Tesla's Autopilot, Waymo's Robotaxi, and Mobile's driver assistance systems all operate on variations of this multimodal architecture. A single Tesla on autopilot can process over 2000 frames per second across its camera array. The deep learning engine never blinks. Now, the trade-offs bottlenecks in deep learning. At this point, you might be thinking, this sounds incredible. Why doesn't everyone use deep learning for everything? Fair question. Let's be honest about the real bottlenecks. Data hungry. Deep learning is extraordinarily data hungry. To train a reliable image recognition model, you might need millions of labeled examples. Labeling data is expensive, time consuming, and requires human expertise. In medical imaging, getting labeled data means convincing a radiologist to annotate thousands of scans, which is slow and costly. Without sufficient data, deep learning models underperform even simple alternatives. Compute heavy. Training a large deep learning model requires GPU clusters running for days or weeks. Training GPT-4, for example, is estimated to have cost tens of millions of dollars in compute. Even inference running a trained model can be costly at scale. This creates a significant barriers for smaller organizations and researchers without cloud computing budgets. The black box problem. This is the most philosophically troubling challenge. When a deep learning model makes a decision, it's often impossible to explain why it made that decision. When a model denies someone a loan, can you tell the customer why? When a medical AI flags a tumor, can a doctor understand the reasoning? This lack of interpretability raises serious concern in regulated industries like healthcare, finance, and law. A whole field called explainable AI (XAI) is dedicated to solving this problem, but is still an active area of research. Understanding this trade off isn't pessimism, it's engineering wisdom. Every powerful tool has constraints, and knowing them makes you a better practitioner. Now, the data scientist deep learning tool stack. So, you want to build a deep learning engine. What tools do you actually need? The modern deep learning stack has three layers, and you can see them visualized here as a literal stack. The foundation Python. Python is the universal language of data science and AI. Its readable syntax, massive library, ecosystem, and strong community makes it the primary language for virtually all deep learning works. If you don't know Python, start here. The core frameworks, TensorFlow and PyTorch. These are the two dominant deep learning frameworks, and they are genuinely powerful. TensorFlow, built by Google, is production proven, scales to massive deployments, and is widely used in industry. Google Search, YouTube, and Gmail all run on TensorFlow trained models. PyTorch, built by Meta Facebook, is the researcher's favorite. Flexible, intuitive, and incredibly good for experimentation. Most cutting edge AI research papers release code in PyTorch. Both are excellent. Many data scientists learn both. The high level API, Keras. Keras sits on top of TensorFlow and provides a simplified beginner friendly interface where TensorFlow requires you to define everything from scratch. Keras lets you build and train neural networks in a dozen lines of code, perfect for rapid prototyping. A real world getting started path. Learn Python fundamentals. Master NumPy and Pandas for data manipulation. Build first models in Keras. Go deeper into TensorFlow or PyTorch for advanced work. Deploy model using cloud platforms like AWS SageMaker, Google Vertex AI, or Azure ML. The tools are accessible, the barriers today is knowledge. And that's exactly what we are addressing together. Now we come towards the future of data science. We started this presentation with an engine analogy. Let's close with it. The quote on this slide says, everything data is the fuel, deep learning is the engine. This is not a metaphor about the distant future, this is a description of right now. Deep learning is already driving breakthroughs in generative AI, models that write, draw, compose music, and generate code, autonomous systems, self driving vehicles, delivery drones, or robotic surgery, predictive healthcare, detecting disease before symptoms appear, scientific discovery. DeepMind's AlphaFold solved a 50-year-old protein folding problem that was blocking medical research worldwide. The data particles you see flowing into the geometric engine on this slide. There's every tweet, every medical scan, every sensor reading, every financial transaction pouring into these deep learning architectures and emerging as intelligent prediction and insight. For a modern data scientist, mastering deep learning is no longer optional. It is the core requirement. The organizations that understand that engine, that know how to feed it, tune it, and deploy it are the ones building the future. The engine is running. The question is, are you at the wheel? Thank you.